Whenever you connect a laptop, phone, or any new computer to a network, there is literally a silent, automated hero working tirelessly in the background to get it online. Today, we're going to visualize exactly how that magic happens. To really appreciate our topic today, we first have to look at the macro problem. Imagine a new device joins a network. At that exact moment, it's completely faceless. It has no IP address. And as we know, without an IP address, it absolutely cannot communicate on that network. So the big question is, how does it get one automatically? Enter DHCP, or Dynamic Host Configuration Protocol. It's an application layer protocol, and its whole job is to dynamically assign unicast IP addresses to devices on a local area network. This is the brilliant, time-saving solution that prevents IT administrators from having to manually type out an IP address, subnet mask, and default gateway for every single device in a building. Could you imagine doing that by hand? No way. So here is our roadmap for this explainer. We'll start by looking at the missing IP problem. Then we'll get a high-level overview of the DORA process. From there, we'll break down DORA step by step, cover some essential DHCP terminology, and finally, we'll talk about scaling all of this up with relay agents.
All right, Section 1, the missing IP problem.
Moving right along to Section 2, Overview of the DORA process.
So DORA is an acronym, and it brilliantly illustrates the overall roadmap of the conversation that happens between a client and a server. It stands for Discover, Offer, Request, and Acknowledge. Just to give you the quick, high-level sequence, the client searches for a server, the server offers an IP, the client requests that specific IP, and the server confirms the assignment. Keep this big picture in mind as we zoom into the actual technical details.
But before we look at the packets themselves, we've got to know how they travel. DHCP operates on a client-server model, and it uses UDP services. Specifically, the DHCP client uses UDP port 67, while the DHCP server uses UDP port 68. You can think of these as the specific logical doors the network uses to pass these DORA messages back and forth.
Okay, Section 3, Step-by-Step DORA Breakdown. Let's really get into it.
Step 1 is Discover. To kind of humanize what's happening here, imagine the client machine shouting into the void of this brand new network, "Hey, anyone there? Is there any DHCP server available to give me an IP address?" Because the client literally has no idea where the DHCP server is, it has to send this message out to absolutely everyone on the local network.
What's really interesting is how that shout is formatted in the packet header. Look at the source IP. It's 0.0.0.0, because, well, the client has absolutely nothing yet. The destination IP is 255, 255, 255, 255, which is the universal broadcast address. It uses its own physical MAC address as the source, but the destination MAC is all Fs. That ensures every single switch and device on the LAN processes this discovery request. Once the DHCP server actually hears that broadcast, we move right to Step 2, Offer. The server essentially replies back, "Yes, I'm available. Take this IP. You can use this IP address."
Let's check out the header for this offer message. The source IP is now the DHCP server's actual IP address. The destination IP is actually still the broadcast address of 255.255.255.255. The source MAC is the server's MAC, and the destination MAC is the client's MAC. But here's the absolute crucial point. Along with the offered IP address, the server is also packaging up the Subnet Mask, the default gateway, the DNS Server, and the Lease Time. It's basically handing over the complete configuration kit.
Now the client receives this kit and moves to Step 3, Request. It formally decides to accept the offer and basically says, "I want it. I would like to use the IP address you just offered me."
And this brilliantly illustrates a really cool quirk in the protocol. Look at the request header. The source IP is still 0.0.0.0, and the destination IP is still being broadcasted as 255.255.255.255. You might be wondering why. Well, because there might be multiple DHCP servers on this network that sent offers. By broadcasting the request, the client is letting all of the DHCP servers know exactly which offer it accepted. That allows the unselected servers to pull their offered IPs right back into their available pools. Pretty smart, right?
Finally, we reach Step 4, Acknowledge. The chosen DHCP server hears the request and seals the deal, replying, "It's yours. The IP address is officially assigned to you." To finalize our microscopic breakdown here, take a look at the DHCP ACK header. Source IP is the server. Destination IP is still that broadcast 255.255.255.255. The MAC addresses reflect the server sending it directly to the client. Once this acknowledgement is received, the client configures the IP internally and can finally start communicating on the network. And there you have it. That is the complete DORA cycle.
Section 4. Essential DHCP terminology.
If you're managing a network, there are 4 foundational terms you absolutely need to know. First, the scope. This dictates the entire range of IP addresses available to hand out. Once an IP is handed out, it's governed by a lease, which is the exact time duration that IP remains valid. Now, if you need to deliberately block certain addresses from being assigned, you create an exclusion. And finally, a reservation holds a specific IP, so it's permanently tied to a specific machine's MAC address.
Section 5. Scaling with relay agents.
When you design a network, you essentially have 2 choices for your DHCP server deployment. You can go decentralized, which means you configure a separate DHCP pool on every single router for every single network. Or you can go centralized, having one single DHCP server handling IP assignments for all the different networks in your enterprise. Now, scaling usually demands a centralized deployment, but there's a pretty big catch.
The catch is that routers by default block broadcast messages. Remember all those 255.255.255.255 destination IPs we just looked at? A standard router drops those immediately to prevent network congestion. So how does a client reach a central server on a completely different subnet? The answer is the DHCP relay agent. This is a configuration feature that allows a router to intercept those local client broadcasts, package them up, and then forward them as direct Unicast messages to a distant central DHCP server.
Let's look at a practical CCNA lab example to see exactly how this unicast conversion works. Imagine your local router interface acting as the relay agent has an IP of 192.168.21, and your distant central DHCP server is sitting at 10.0.0.1. The relay agent intercepts the local broadcast, creates a fresh message, and unicasts it directly from source IP 192.168.21 on port 68 straight over to destination IP 10.0.0.1 on port 67. The central server replies, the relay agent passes it back to the local LAN, and boom, the distant client gets its IP.
It really is an incredibly elegant system. As enterprise networks scale toward these massive, automated SD-WAN environments, this invisible process saves us from literally thousands of hours of manual configuration every single day. But as we put more trust into these centralized servers, what happens when a rogue DHCP server gets introduced to the network? Well, that is a security vulnerability for another day. Keep visualizing these concepts, and I'll see you in the next explainer.